This program is brought to you by Stanford University.
Two speakers we have today from the Department of Material Science and Engineering, Professor Mike McGehee and someone just, so Mike is going to begin.
Thank you. So good afternoon. I'm here to tell you about the new Center for Advanced Molecular Photovoltaics. It started just a few months ago in July. And I'll tell you a little bit more in just a few minutes about our technological goal. But first, let's talk about where the money came from and why they gave us this money. So we get $5 million a year from Saudi Arabia. And certainly you're thinking that's a lot of money, and that's an unusual source to get funding from. So why is Saudi Arabia giving us all this money? Well, they are launching a new university, the King Abdullah University for Science and Technology. The King of Saudi Arabia put up an endowment of $20 billion for this university. So I think they have the world's third largest endowment already. The campus is not even built yet, but they have the third largest endowment. It's going to be a revolutionary university in quite a number of ways. And it's going to be the first university in Saudi Arabia where women and men are going to be educated together in the same classrooms. Most of the restrictions that exist throughout Saudi Arabia will not apply either at the university or the town that they're building around it. The university is not really trying to copy the other great universities of the world. They are trying to build the ideal university for right now. And they're looking at areas that are emerging. They're not, again, not trying to copy industries and technologies that are already successful. They're looking at emerging areas, and I think these are areas that are of great interest to most people here. So energy and the environment is, I would say, by far the biggest research topic there, but they're also interested in the biosciences, material science, and computation. They only have a graduate program, so they don't have all of the undergraduate departments. This is a picture that I took when I was over in Saudi Arabia in May. There were about 100 cranes at that time and about 20,000 workers working 24 hours a day in rotations. This is what it looked like just 1 month after I took my picture. So this is coming along at a much faster clip than our new building. And this is what the university will look like, hopefully by September of next year when they open on September 5th. So it's a very exciting project. But maybe I still haven't answered the question, why are they sending $5 million a year for the center at Stanford? The other thing that's revolutionary about this university is that they want it to be truly international. They want it to be a place that brings together researchers from all around the world in a global research partnership. And so they have reached out and had a competition from top universities around the world, and we were fortunate to be one of the ones that was selected. And they want us to be partners. They want us to help them recruit the best faculty. They want us to help them get some of the best students to come there. They wanted our feedback on what they should put in these buildings, what kind of equipment they should have. And when I was over in May, I have to say it was a lot of fun to have someone say, if money truly was not an object and you could build whatever lab you wanted, what would you build? And you start talking to each other and you say, well, you know, 4 or 5 TEMs would be nice. And someone says, no, we don't need that. And then they interrupt, don't worry about it. If you want 5 or 6 TEMs, tell us that we need 5 or 6 TEMs. So the labs are going to be really quite amazing. Part of our partnership is I will be going over there on sabbatical, and students and other faculty are encouraged to come over for visits of anywhere from a few days to a quarter, or of course we'd love to have students go on to be professors over there. And as you can see, it's right on the Red Sea, and they say some of the best diving in the world is out there, and good sailing as well. So I think it's going to be a really exciting project, and if you're interested in participating in this, even if your research interests were totally different from what I'm going to talk about today, I could put you in touch with people over at KAUST. But then there's another really exciting goal that our center has, and if I would capture it in one picture, it would be this. We want to make it possible to cover about 1% of the land on the planet with solar cells that have an efficiency of about 15%, so that you could provide the world with all of its electricity just from solar cells. And every week you hear different technologies, and I don't know if we will use solar fully to this extent, but our center would at least like to make that available as an option for solving the world's energy problems. So that's what we're trying to do, and I think that it's possible that this could be done with silicon solar cells, but right now the cost of getting electricity from silicon is 3 to 5 times higher than from other means, and I think those costs are going to come down, but I don't think the cost from silicon solar cells is ever going to match that of a coal-fired power plant. So we're trying to change the paradigm. We want to make it possible to print solar cells in a roll-to-roll coating machine like you see this. So instead of taking very high quality crystals of silicon and dicing them and polishing them and making cells, we want to print them more like the way you make newspaper or photographic film. We want the substrates to be flexible, so that they're fairly durable and easy to install, something that you could just roll out on a roof and secure. We want to manufacture it at high speed, and we want the materials to be cheap. And this is where molecular semiconductors come in. This is just another way of saying organic semiconductors. So we're using molecules that have alternating single and double bonds. And these molecules can have semiconducting properties very similar to those of silicon. This is an example, copper phthalocyanine, and it's already a widely used molecule. It's used in blue car paint. It's manufactured at about 100,000 tons per year. And when you look at what the cost would be if you incorporated this into a solar cell, it would come out to be about 17 cents per meter squared. And right now, a silicon cell costs about $350 a meter squared. That's for everything. And we're targeting a total cost of $30 per meter squared. So you see the material costs would be a very small fraction of the overall cost if we were using a material like this. And this material is not limited by any rare elements. If you look at some of the other attractive technologies like SiG solar cells and cadmium telluride, in SiGs you have indium, and I think there's enough indium for the startup companies out there to make even a few $1 billion, but I don't think there's enough indium out there to provide the world with terawatts of power. So we're going to need to move beyond that, and here we have a material that will not be limited by material availability. And finally, it's worth pointing out that this is a non-toxic material, and cadmium telluride is based on cadmium, which is toxic. So where does this technology stack up against the other solar cell technologies? This is a really cool graph that plots the record efficiency of most of the well-known solar cell technologies as a function of time. And if you look at the champion up here, these are the multi-junction cells, and the record is now above 40%. And of course, the reason it's not clear that we want to use those is the cost is about $50,000 a meter squared because you've got different layers of crystals grown one atomic layer at a time in a very expensive epitaxial process. If we do employ these, it will almost certainly be with large concentrator systems that need to track the sun. So some people believe that's the way to go. Silicon right now, the record is at about 24%, but when you buy large modules, it's typically at about 12%. And that took about 50 years of development for silicon to get to where it is. And that was piggybacking on the computer industry, which also uses silicon. So I think it's important to realize how long it took to get there. And then SIGs is up at about 20%, and cadmium telluride is about 17%. So the organics, right now, the world record, on this plot it's shown as 5.4. Plextronics just moved that up to 6.2. So we're at about 6.2% right now. But it's a very new approach. And what I want to show you today is that we're developing an understanding of what holds that efficiency back. And we have plans to push up we think with just one semiconductor, we can get up here to almost 15%. And we think we can go above that by stacking layers that absorb different parts of the solar spectrum. So what are our goals more specifically? We want to get an efficiency of about 15%. Of course, we'd like higher, but we think that this is a realistic value that we can obtain on the 5 to 10 year time scale. That would compare to what you see out there right now on most people's roofs. If they have cells, they're typically at about 12%. So we're not really, and to be honest, that number will climb to 15. So we're not necessarily trying to raise efficiency. We're hoping to get a lifetime of 10 to 20 years and maybe eventually 25. And again, we wouldn't be beating silicon there. But where we really hope to win is in cost. We think we can bring the cost down to about $30 a meter squared, which would be about a factor of 10 lower than where silicon is. And I think still a factor of 3 or 4 lower than where silicon will be someday when it's fully optimized. But I also want to emphasize that the biggest goal of our center is training really good students who go out into the industry and work on either molecular solar cells or other kinds of solar technologies as well. So now let's get into how do these solar cells work. In some ways, they're similar to conventional solar cells, but in other ways, they're really quite different. The first thing that happens is light is absorbed by the semiconductor, and then you get an exciton, and that's a bound electron-hole pair, and that's where the physics diverges away from what happens in a conventional solar cell. In silicon, the electron and hole are not bound to each other. They immediately become free particles, and you can try to pull the electron to one electrode and the hole to the other. But here, they're more strongly attracted to each other, and they remain a bound pair. So what happens is the exciton diffuses to an interface between two semiconductors that have offset energy levels. And when it gets there, the electron can transfer over to the semiconductor with the lower lying conduction band. And I should add that these are the band gaps. So the top is the conduction band, and the bottom is the valence band. And then after that happens, the electron can come out to one electrode, and the hole can come out to the other. So we've essentially used two semiconductors to help separate the electron and hole. And it's interesting to note that this is exactly what happens in photosynthesis. After light is absorbed, to keep the electron from rapidly falling back down, it undergoes electron transfer to a different part of the photosynthetic complex. So now I'll start talking about the team and what we'll be doing. And as I go through the talk, you'll see what most of the people in the center will be doing. There are 3 of us who primarily work on solar cells. We make them, we test them, and we use models to understand what's limiting the performance. That's myself, Peter Poymans, who's also the deputy director of the center, and Michael Gratzel, who is at EPFL over in Switzerland. So one of the keys to making these cells work well is that you have to pattern the 2 semiconductors right at the nanometer length scale. So here you see an example that can be made by blending a semiconducting polymer. Those are long chain-like molecules with fullerenes, which are little balls of carbon that look like a soccer ball. When you dissolve them together and cast a film, you can get a structure that looks schematically like the one you see here. And then you see no matter where light is absorbed, the exciton is going to be near the interface, and therefore you can split up the excitons. And then the challenge becomes having an architecture that allows the electrons to have a pathway to one electrode and the holes having a pathway to the other. So this is the approach that my group primarily uses. We use polymers, and we think the advantage is that they can be dissolved, and the solutions have about the right viscosity for various printing techniques. So we never have to go into a vacuum chamber when we deposit these materials. There are a lot of things that I could say about the work, but I'm just going to give you a 2-slide highlight just as an example of what we do. So recently we saw some strange behavior with one of these polymers, and we found that when we had half polymer and half fullerene, the solar cells hardly worked at all, and with other polymers, that was actually the best ratio. So we collaborated with Mike Toney up at the synchrotron and used X-ray diffraction to learn how the molecules were packing. And to make a long story short, what we learned is that for some polymers, there's enough space between the side chains for the fullerene to insert itself in between there. And then for other molecules, there's not enough space. And so it turns out that when the molecules go in there, that is, of course, really good for exciton splitting, because the polymer chains are right next to the fullerenes. On the other hand, it's not so good for separating electrons in holes, because as the electrons work their way out of there, they're right next to the holes. And so the recombination, or you could think of it as the backward electron transfer, can be kind of fast. So there's both an advantage and a disadvantage of having the molecules mixed right at the molecular level. So here's an example of a polymer where you don't get this intercalation, and then you have well-defined crystals of just pure polymer and pure fullerene. And we find that works really well as long as the crystals are small enough for the excitons to make it to the interface. So if they're about 10 nanometers across or smaller, we find that this works really well. The other thing we've learned is that when you don't have the mixing, it's best to have about a 1-to-1 ratio of the 2 components. You want to have an equal volume of hole transporting material and electron transporting material. But when the fullerene goes in between the side chains, then you need about a 1-to-3 blend, because you need 1 part to mix in with the polymer, and then you need 2 parts so that there's this pure electron transporting phase that matches the volume of the hole transporting phase. And if you lose that balance, then one of the phases can surround the other phase and confine charge carriers in there. So that's just an example of what our team is able to learn by using our advanced characterization techniques. And going forward, Jerry Fuller has come onto the team, and he's in chemical engineering, and he's an expert on the viscosity of materials and how they flow, and he'll be studying how we can modify the processing to better control things like the orientation of these crystals. So now I'll give you one highlight of Peter Poyman's work. So his approach is a little bit different. What he does is he takes molecules that are smaller than the polymers, and he evaporates them in a vacuum chamber. So a disadvantage is that you have to go into vacuum, but an advantage is he doesn't need these side chains. Those side chains are insulating, and we're forced to put them on to make the polymer soluble. So he can get away from that, and some of his molecules can have better properties, but perhaps the processing is a little bit more expensive. I think one of the most exciting discoveries that his group has made in the last year or so is they figured out that a lot of the polymers, a lot of the molecules people were using were doped, even though they had not done that intentionally. There were undesired impurities that were doping the material. And what that ended up doing is concentrating the electric field at the interface. It created a PN junction. And then they found when they purified the materials, then they lost the doping, and now the electric field would be spread out over the entire film. That actually turns out to be bad. When the exciton splits, you have an electron right here and a hole right there, and you want to pull them apart, and so that's where you need an intense electric field. So it's actually best to dope the materials and split your excitons. And so perhaps I should not have said that the dopants were undesirable. In fact, it turned out that those impurities were a good thing. And now that they understand this, they can purify the materials and then put in a dopant at a highly controlled level to optimize the performance of these solar cells. Now I'll tell you about the third approach we have to making solar cells. Michael Gratzel has an approach where a paste of titanium nanocrystals is deposited on a film, and then they are covered with a dye that is able to absorb light. And after light is absorbed, an electron is transferred from this to the titania. So the TiO2 is just one of the semiconductors. And then there's a third molecule, spiroomatad, that takes the hole off of here. And so basically one molecule's job is to absorb light, the titania's job is to pull electrons out, and the spiroomatad's job is to pull the holes out of the device. So it's just a different approach, and right now the world record efficiency here is 5%. So interestingly, all three approaches are approximately tied with each other at the moment. So here's our plan for making these cells better. We find that if the cells are much thicker than about 2 microns, we're not able to pull all the electrons and holes out. There's recombination, and the thicker the cells are, the harder it is to collect the charge. But we need to make the cells thicker to absorb more light, unless we use this new approach. And the new approach is that we add these dyes shown in red that we call energy relay dyes. And so they absorb more light, and then after they absorb light, they're able to relay the energy to the sensitizing dye, where you then get electron transfer and charge transport. So essentially, we've taken advantage of some dead space. The spiro was only transporting charge. Now we've added something that can absorb more light, and so a thin film can absorb more light, and it also can absorb over a broader spectrum. We can design this to absorb the higher energy photons and let the other dye absorb some of the lower energy photons. Another approach we're using to improve these cells is Stacy Bent is going to put a very, very thin barrier on the titania, and it'll be so thin that it will not block the desired forward electron transfer, but it will slow down the back transfer. And it turns out that the forward transfer is faster than it needs to be, so you can slow it down a little bit without hurting the performance, but slowing down recombination will be very helpful and should boost the efficiency of these solar cells. Then we have some approaches that apply to all of these solar cells. We think that there are really exciting opportunities to use new advances in optics. And Peter Poijmans has already done some work in this area. And Mark Brongersma and Shanhui Fan have groups that really specialize in advanced optics rather than solar cells. And they will be helping us to do things like use metal nanoparticles that you could think of them as antennas that help boost the absorption. And so similar to the last project, what that could do is allow us to use thinner films. And whenever the films are thinner, it's easier to pull the electrons and holes out. And so we should be able to boost the efficiency on top of not having to use as much material. So if our center is going to be successful, we not only have to boost the efficiency and deposit the semiconductors at low cost, we also have to deposit the electrodes at low cost. And currently, when people make these solar cells, they use indium tin oxide. It's the same electrode used in all of your laptop displays. But there are some issues with it. It doesn't work quite as well as you would like. You have resistive losses as the current passes through the ITO. The cost is about $10 a meter squared, and our target for the whole thing is $30 a meter squared. So you really hate to sink a third of your cost just in the substrate and the electrode. Furthermore, ITO is brittle. You can bend it a little bit, but it slightly complicates using roll-to-roll processing, and it introduces weakness in the final product. So we'd like something that is flexible and that is compatible with plastic. And part of the problem there is ITO is deposited at 400 degrees, so the plastic substrates we would like to use can't handle the ITO deposition. So the solution that we propose here is using various kinds of nanotubes or nanowires instead of the ITO. So here you see a mesh of carbon nanotubes. Nanotubes conduct current, I think probably as well as any material that we know of. And so extremely small nanotubes, just 1 nanometer across, can carry a substantial amount of current. And consequently, we can have very, very light coverage with the nanotubes and get the conductivity that is needed. And because there's so few tubes, the absorption is relatively low. So here you see a flexible solar cell that we've made in my lab using the nanotubes. Right now, the cells with nanotube electrodes are almost as good as those with ITO. They're only about 15% worse. And so if we could improve these a little bit, we would possibly be able to replace ITO. Yi Cui and Peter Poijmans have a similar approach. They are using silver nanowires, and the silver nanowires contact each other better than the nanotubes, and so that's one advantage they have. And they have recently shown that they can make films that have actually almost exactly the same properties as indium tin oxide. And you can see that these are highly flexible films as well. And the transparent part is right here in between two traditional metals. So you see that it's both transparent and it has a sheet resistance that's about the same as indium tin oxide. The only problem with these films, the wires are fairly fat, and the spots where the wires cross are thick, and that can kind of punch up into the solar cell a little bit. And Alberto Soleo has a third twist on this. He's using zinc oxide nanowires. Zinc oxide is inherently transparent. It doesn't conduct as well as silver, but it's much more transparent. And so this could possibly be the way to go. Currently, these films are a little bit more resistive, but the work is still in the very early stages. And the doping level, for example, has not been optimized yet. What Alberto finds is that these films are milky, and that's because they scatter the light. And while that may seem bad, it could actually be very good for a solar cell because you like to scatter light into the plane and have it travel horizontally through the solar cell because then it will almost certainly be absorbed, as opposed to when it goes through vertically and it only has a short distance in the film to be absorbed. It's also intriguing to think about combining zinc oxide with silver and carbon nanotubes because they each have their own advantages. So it might be that a hybrid will give us the optimal electrode. So now I'd like to hand it over to Alan, who will tell you about the molecular design.
Tandem talk here. So yeah, I'll go into some more details related to the molecular design and chemistry. So Lee assured me that the audience were all organic chemists, and so you'll be able to understand some really detailed topics here. So as a chemist, traditionally we are just going off and scribbling some ideas onto some back of the envelope and then go ahead and try to synthesize the compounds. But now we're realizing that it's a big advantage to have help from computation. So, So we have brought in Jean-Luc Breda from Georgia Tech, and he's an expert in this area of quantum chemical calculations. And so, for example, as a chemist, you could think about many different things to make. And so here, in just this example, we have this X group, which can be either carbon, silicon, or nitrogen, and then this Y group, which could be any number of these 9 compounds here. So we have 27 different options here, 27. So you can imagine trying to make over 100 of these kind of materials. And if you're a chemist, especially a polymer chemist, you know that there's, within each of these materials, there's all kinds of different variables. There's residual catalyst, there's defects in the polymers, there's all kinds of issues that you need to worry about. So when you're designing these materials, then it's a huge advantage to have somebody who can simply plug all of these into a computer and come up with a way to calculate some of the energy levels that are really important for this application. So, for example, if you want to have a certain material that has an energy level that will match with another acceptor that you're interested in, then this is a really good way to screen the materials, so you can just simply go for the type of energy levels that you need and go from there. Also, when you deposit these materials, of course, they will be at in solution, they'll be far away from each other, but as you make these thin films, they will become closer and closer contact with each other. So now you have these molecules that are approaching each other, and they have these pi orbitals that will interact with each other, and those will cause splitting, and this can even be calculated as well. So there's all kinds of course, I'm only showing a few slides that Jean-Luc is doing, but he's helping us in many other ways as well. Yeah, so now is the part that everybody will enjoy, because I'll be going into some details of synthesis. So on the team, we have Zhenan Bao, who's here at Stanford. We have Mark Thompson from USC, Jean Trichet Berkeley, and myself. So in this area, as Mike explained, there's 2 types of materials that are used in organic and polymer solar cells. One is the P-type material, and if you look further, you'll see that about 90% of all of the new materials development is in this P-type area. So there's not much work going on in the N-type area for various reasons, because it's a very difficult area to work in terms of finding new materials. So this is one of the topics that we decided to pursue. And so here I'm just briefly showing some of the design and strategy for a particular molecule. So here we have a system that is very electron deficient, so that means it can accept electrons. These electrons can be delocalized within the molecule because we have introduced these vinyl groups which allow for electrons to move within the molecule. And we also have these groups on the side that Mike mentioned can be used for solubility. So in this case, we can use this in solution processing if we make these quite large, or if we make these small, we can actually sublime these and use these in small molecule solar cells. So they're fairly versatile, and so here just showing that in one case we have 6 carbon chain, and if we add a 2 carbon chain off to the side, turns out that that's much more soluble and can be used in other types of systems. So now we go ahead and make solar cells. We combine these new acceptor materials with a known donor polymer that we can simply buy. We make devices, and one of the things that we're targeting is open circuit voltage. So in this case, we can improve open circuit voltages over some of the more traditional materials matching, which are usually in the 0.6 to 0.7 range. And then we can further extend this type of VOC just by selecting another type of donor material. So this is basically a way that we can tune open circuit voltage, and now we're looking at a lot of the issues like Mike was mentioning, morphology and other things to optimize this even further. So Mark Thompson also is interested in this area, looking at VOC. So in this case, we have a donor and acceptor, and this IG is proportional to the VOC. So he is also working with different donors and acceptors and trying to move around this value. So here in this complicated slide, we have this CuPC, this copper phthalocyanine that Mike mentioned earlier in the talk. And then by introducing different materials into the acceptors side, we can change this IG, which in turn change the open circuit voltage. So in the next slide, you can see that by changing the materials combination, he improved the open circuit voltage from 0.4 to almost 1 volt, and that in turn improved the power efficiency of the device. So this is another way to work with certain parts of the energy levels to increase the performance of your device. And here's another slide I'm sure many of you will enjoy, but basically what we're trying to show here is in Jinan Bao's group, she's able to do very nice designs of the molecules that will allow the materials to absorb further into the higher wavelengths, which is what you want. You want to have these materials absorbing more of the solar spectrum. So she is just systematically changing parts of this molecule and pushing this in the direction that you want. So this is a really a neat approach, and this will, I'm sure, lead to some really nice devices in the future. She's also been working in the past in these fused systems where traditionally these are really insoluble and can only be used in vapor deposited applications. But now she's been able to link these up into polymer systems and to use these for making solar cells also that can be improved upon. And the last example here is basically going into morphology. So I've been talking about energy levels, but now you can look at morphology. So turns out if you make certain materials, you have a different level of crystallinity in the solid state version. So you have one material that you can polymerize and you can make these things very crystalline. So this RR is just referring to crystallinity. You can plug in certain materials in that polymer backbone and you can systematically reduce this crystallinity. And so it turns out that when you just deposit these materials at room temperature, the one that has the higher crystalline material is more efficient in the beginning, but as you heat it up, in terms of, this is kind of like an accelerated aging study, you can see that in the end, the one with the least crystallinity is the one that provides the best performance. So in the past, it was thought that you need to have a really crystalline material in order to make a better device, but in Jean Frichet's lab, he showed that it's actually the opposite. Now we're looking at lifetime issues. So of course, we're going to have to make these things last. So one of the traditional ways of looking at this, so again, Mike was talking about flexible devices. So in a flexible device, you have a lot of different issues. From just the bending and flexing of this device, you have issues that could be forming at the interfaces. There could be debonding, there could be cracking. The flexible substrate itself, water and oxygen can diffuse through it. So even in just the plastic bottles that we're drinking our Cokes out of, these will not work at all in terms of just as a barrier substrate. So the water and oxygen that will go through that kind of thickness of plastic is enough to kill these devices in just a few hours. So there's a lot of technology that's going into barriers, films that are put onto plastic substrates to help with this issue. And that's been the traditional way of looking at this. And this is another group that we're developing within our center. But there's also this mechanical issue. So what happens when you flex this? Where is the failure occurring? And this is work done in Rainer Dasgaard's group here at Stanford. So if you look at the cross-section of a typical device, there's ways that you can stress this device. So he is taking this and basically shearing it or physically trying to peel this away and then going back and looking at what happened as a failure mechanism. And so surprisingly, you would think that the failure would occur at an interface. And this is traditionally what happens, but Rainer found that in fact the failure is happening within the active layer of the device. And so he can analyze this just by reverse engineering, looking at the surface and seeing what's there. And so this was an interesting discovery to show, and this will also help us in the future for maybe we need to think about other types of material combinations to make it so that the failure is not occurring in the active layer. So I believe that is the last slide. So I think Mike and I have been trying to relay the fact that there's a lot of exciting new research going on in this center. I think one of the most important aspects is that this is very interdisciplinary. So we showed, the chemists, the physicists, the engineers, all of these people are working together. And I really don't think there's a center in the whole world that has combined this type of expertise into one area. So we really have a very good opportunity here to make a lot of progress by working together. So of course we'll be working closely with KAUST in Saudi Arabia, so there'll be a lot of opportunities in the future potentially for student exchange and aspects like that. And the last item I show is just the contact information. So here I put myself because I think if I put Mike on this slide, he would come chasing me later. So yeah, that's the last slide, and I thank you for your attention.
So we have time for questions.
Yeah, I assume right now the samples are fairly small, and I'm wondering what you see as the challenges in trying to scale up to larger size. You talked about what is going to be achieved in meters, line size. What would be the challenges involved with this technology for that?
Right. Well, so you're right. Here at the university, our substrates are rarely larger than 1 by 1 inch, and we don't plan to scale up at the university. But companies like Plextronics and Kanarka are starting to look into this, and I've seen Kanarka make cells that are about a foot wide. It's not one individual cell, I should say, modules, that are several feet long, and so they're using a printing process, and it becomes very similar to. I think photographic film might be the best established industry, because photographic film has about 12 layers in it. That's color film, and those layers have to have pretty precisely controlled thicknesses. And so, of course, that industry has tanked rather precipitously in the last 5 years. So literally, a lot of the people who left that industry are now working in the organic solar cell industry. Not a lot, but a handful of people are carrying on that knowledge.
Question in the back.
What are some of the challenges before this technology can be commercialized?
Well, you know, I mean, we went through a bunch of them, and you know, the short answer is you know, efficiency, lifetime, and cost, and the efficiency needs to go from 6 up to about 15%, and I guess we weren't able to get into the full details, but right now we don't have good low band gap options, so we're not absorbing the infrared part of the spectrum. When we make our cells thick enough to absorb the light, even where the semiconductors do absorb, we're not able to pull all the electrons and holes out. So you saw a couple of our strategies for either improving that or making thinner films absorb better. You know, moving on to lifetime, the cells only last a year or two right now, so we need to boost that. But it's worth noting, when I was a graduate student, I worked on organic light-emitting diodes. And to test them, if you wanted to see it, what you would do is turn the lights off in the room, let your eyes adjust to the dark, because you turn it on and there'd just be this short flash of light, and then that was it. The device was dead. Well, you know, once industry took over, they got the lifetime up to 50,000 hours very quickly. And it's just a matter of purifying the materials, and some molecules are more stable than others, and so you know, it'll be a challenge, but I think a lot of progress can be made. And then I think the $30 a meter squared is the easiest of the three, but still, and you know, until it's actually done, you shouldn't just assume that it can be done. And it's you know, I've watched a lot of industries now, and looking at the solar cell companies out there, and you know, you easily go through $500 million building a fabrication line that can you know, do this stuff and you know, spit out solar cells where 99% of them work the way they're supposed to. So you know, those are the three big challenge areas.
Just a quick follow-up. Do you see any challenge to production? Large-scale production?
Well, that's. I mean, I think it's very doable, but people should be very realistic that, you know, it's going to take 100 to 200 people 3 or 4 years to build this equipment and get it. You know, they will get a prototype very quickly, but to get to a point where you can, you know, manufacture you know, very, very large quantities of solar cells cost effectively, it'll be a lot of work. And you know, that right now the SIGs companies primarily are finding out how hard it is. And I mean, this is true of any materials-based technology, that perfecting it requires a lot of work.
And I wanted to add something there. So, like Mike mentioned, this is also related to organic LEDs. So organic LEDs are, you know, currently there's some products on the market. And in that case, there was a difficult transition from R&D to manufacturing in terms of like product yields and things like that. But in the case of OLEDs, you have the other problem, whereas if you have a display sitting in front of you and you have 1 pixel in your display that's not working, then as a customer, that device is gone. You know, it's a failed device. But of course, in a solar cell, this is not going to be the issue. You know, you won't be able to detect that kind of loss. You know, so I think there's even a little bit more play that can be in the solar cell versus the LEDs.
Could you discuss the degradation methods of these organic compounds with ultraviolet?
I mean, so organic molecules, yeah, they are sensitive, but usually that's in an environment where there's oxygen around. So if you have these devices encapsulated properly and there's no oxygen there, they actually do quite well. So for the flexible devices, of course, it's a big problem in terms of this permeation issue. And in that case, it's usually found that it's the electrodes that are more susceptible to failure than the organic material.
Okay. You mentioned that the carbon nanotubes and the silver nanowires could be good alternative surface electrodes for silicon oxide. Could those be applied to existing solar cells pretty easily, or your thoughts on that?
Yes, they would be unnecessary on a crystalline silicon solar cell. There is no transparent electrode on those. The silicon on the top is highly doped, and it's just an extremely good charge transporting material, and so the silicon itself carries the current out to very thin silver wires. I think there is great interest in using those electrodes on thin film solar cells like amorphous silicon SIGs and cadmium telluride. And if you look in the literature, you'll find demonstration papers for at least SIGs and cadmium telluride. For the carbon nanotubes, the silver nanowires were just developed very, very recently here.
So one last question, your choice, Mike.
No, you've been waiting.
I noticed, well, even at the $35 a square meter and 5% efficiency, you're still about 60 cents per peak watt. So people like First Solar are kind of closing in on you at $1. Also, if you stay at 5%, large area of this stuff, to get up to the 5 to 10 kilowatts that you need for, let's say, a house or something like that. So the basic thing is to really get it up from like 5%. And I noticed, like when you showed your slide, your fill factors were something like 0.5. So your charge transport and losses are probably the thing that you want to work on. What's the prospect?
Well, I have an hour-long talk that addresses that the charge transport issue, and I mean, first of all, commenting on the first part, I don't think we have anything at 5%. I think we have to get to 15%. There are people who disagree with me on that, but I think you're right that the areas become so large that it's just not very feasible when you're at 5% efficiency. So you have to get to 15, and we've basically shown that the essence of the problem is that when the electron transfers over to the acceptor, it is still attracted to the hole, and you need a fairly strong electric field to pull them apart. And as the voltage approaches the open circuit voltage, there is hardly any electric field left in the device. So what you're trying to do is extract the carriers with a very small field. That's the only way to have high voltage and high current at the same time. So there's a couple directions you go. First of all, you've got to try to keep the cells thin so that the voltage is dropped over the shortest possible distance so that the field is a little bit higher. So you saw some of our strategies for keeping the cells thin. Then you have to reduce the probability of the electron and hole recombining. That's where the thin barriers that Stacy Bent can deposit come in. They would just prevent the recombination. And another approach is you raise the dielectric constant, which reduces the attraction between electrons and holes. So we have kind of a three-pronged approach at tackling that problem. And I guess I never actually showed data for our best cells. We can do fill factors of 0.7, so I'm optimistic. Although we can do 0.7 in a 200 nanometer thick film. When the thickness goes up, the fill factor goes down.
Very good. Well, thank